Okay, we're going to carry on with this lesson. We're still on the chapter of transistor bias circuits. Going to carry on with section 5.2, specifically on the voltage divider bias. Now, the voltage divider bias, if we can refer to the textbooks, mark the introductory paragraph. You will now study a method of biasing a transistor for linear operation using a single source resistive voltage divider. This is the most widely used biasing method. We will see a bit later on why. And then, of course, the other methods will also still be discussed. But firstly, up to this point, a separate DC source VBB was used to bias the base emitter junction because it could be varied independently of VCC, and it helped to illustrate the transistor's operation. Remember what we've done? We have adjusted in the previous section the separate VBB so that we can get the different curves for each different IB. And then finally we established using the cutoff and saturation points drew the load line, and then we also saw that, okay, specifically we want the Q point to be in the middle of the load line so that we can have maximum swing of my input signal. Remember, I want to use it for linear operation. Alright, so in this case now we can see that I'm using a single supply called VCC, still called VCC, and it's now simplified by just a single point. Previously it would have looked like this. If I complete the circuit, there's my VCC. So it's still the same thing. It's just to simplify the circuit that they're using a single point for VCC. So remember that we are still looking at the current flowing in that direction for the circuit, and we're still looking at that part of the circuit at the base where the base current is flowing. And we can see again here the three currents here, IC, IB and IE. I can still see then that IC and IB, if I add them together, it will become IE, which is the largest of them all. But remember, they only differ by the value of IB, which is very small in comparison. So you'll see sometimes we assume that IC and IE are the same, although they're not exactly, but they're very close to each other because IB is very small in comparison. Anyway, if we go back to the textbook, I've marked there, generally, voltage divider bias circuits are designed so that the base current is much smaller than the current I2. That's the current running through R2, if you refer to figure 5.9 in your textbooks. In this case, the voltage divider circuit is very straightforward to analyze because the loading effect of the base current can be ignored. A voltage divider in which the base current is small compared to the current in R2 is said to be a stiff voltage divider, because the base voltage is relatively independent of the different transistor and temperature effects. Okay, so if I go and look at the voltage divider circuit as we have here, remember, I have to determine VB. Where is VB? Let me just go back to my circuit there. VB is the voltage at the base. Remember, previously we had a separate supply here and not a voltage divider. I had a separate supply here, VBB, and most recent we had an adjustable power supply there. And as I adjusted this voltage, I could adjust IB. So that's how I determined to get, remember, my characteristic curve of IC against VCE. Remember, those were the parameters for cutoff and saturation. Then I could adjust. If there was no IB, of course, then I know that IC is equal to 0 and VCE will be equal to VCC. And if it is in saturation, I know that the maximum current is flowing. Remember, we've seen that maximum current flowing is called IC sat, and it's determined by the maximum voltage and the voltage drops to get the maximum current. So I got a point there that's called saturation point, and I connected these two. That was called the load line. For amplification, I know that I want to operate between cutoff and saturation for linear operation. Then we've seen by adjusting VBB, I could determine a certain IB, which I called IBQ because it determines my Q point. Remember, where it cuts my load line, that is the Q point. Okay, and we wanted it to be in the middle of the load line, or as close as I can get it. Anyway, to get back to the voltage divider bias. Remember now, I've got rid of VBB. I'm using a single supply VCC, and I'm now using a voltage divider. What does a voltage divider do? Exactly what it says. Remember, I want VB. So to determine VB, what does the formula say? Voltage divider says I must get the ratio of the two resistors, R1 and R2. If I want the voltage over here, remember if VB is here, it's the base. So VB is going to be here. Single subscript is measured with reference to ground. So I'm measuring the voltage between base and... So I'm measuring the voltage between base and ground. Ne? So it's with reference to ground. So it's actually the voltage over R2. So VB and VR2 is exactly the same thing. But we talk about VB, the voltage at the base, because I want to determine my Q point. Remember, I have to bias first before I amplify my signal. Alright, so voltage divider formula says if I want the voltage over R2, then the R2 is on top over the total resistance, which is R1 plus R2. That's going to give me my ratio, and the multiplied with the supply voltage, which is VCC. Okay, that determines my VB. Those formulas you will find on page 223 at the bottom of the page. This is equation 5.1. Alright, then we also know, what am I looking at this stage? What is the condition for the transistor to be used as an amplifier? The base emitter junction must be forward biased, base collector junction must be reverse biased. So I'm looking at this series circuit now. So the base emitter junction, there's the base, there's the emitter. We know that there's a voltage drop. We assume to be approximately 0.7 volt. So if I want to determine, I have determined VB. If I want to determine VE, then I know there's a 0.7 volt drop that I have to subtract from VB. Okay, that is equation 5.2. So VE is equal to VB minus VBE, which we assume to be approximately 0.7. It's not always true, but we make that assumption. Then here, the last equation on that page, equation 5.3, you can see that IC is equivalent to IE. I make this statement, IC is equivalent to IE. I can make this statement because I know IB is very small in comparison with IC and IE. When we discussed these currents in the previous chapter, we saw that it is a lot smaller than these other two currents. So I make this assumption, and then I can calculate IE by using Ohm's law. I is equal to V over R. I've just calculated V, which is VE. I have the value of RE, so I can just use Ohm's law to calculate IE. Alright, what else do I need to calculate? VC. What is VC going to be? Voltage there at the collector. Value of VC. Use Kirchhoff's voltage law. I know Kirchhoff states that the sum of all the voltage drops around the circuit should be equal to the supply voltage. My supply voltage is VCC. I want that voltage there. So if I look at the current flow in that direction, where is a volt drop? Over RC. So I can see that VC is going to be VCC minus the volt drop over RC. Then I have the voltage on the collector. Alright, Now I've determined all the terminal voltages. Remember, they are called terminal voltages. The transistor has three terminals: collector, base, emitter. I've calculated VB, I've calculated VE, and I have calculated VC. Now I can ask you to calculate VCE for me, for instance, or I can calculate the voltage between any three of these terminals. Because what is VCE going to be? VCE is going to be equal to VC minus VE. What is VBC going to be, for instance? Let's have a look at that one. VBC, the base collector junction, we know should be reverse biased, né? So VB is going to be equal to, I read from left to right, is going to be VB minus VC. Is this going to be a positive or a negative voltage? What is the size of VB? It's going to be smaller than VC. Né? That's why I get the base collector junction to be reverse biased. So the answer to VBC is going to be negative to indicate that it is reverse biased. If I read VBC, remember, if I change it around and I ask you to calculate VCB, we read from left to right, then it will be VC minus VB, which is going to give me a positive voltage. So just keep that in mind as well. But let's have a look at the example 5.2 there in the textbooks to see how this, should we say, a stiff voltage divider biasing is calculated. The question asks there, determine VCE and IC in the stiff voltage divider bias transistor circuit in figure 5.10 if beta DC is equal to 100. So here I can see is my voltage divider. I know I have to apply the voltage divider formula as we've just seen. So it's going to be VB. VB is going to be equal to R2. Remember, I want to calculate the voltage drop over R2. That should be on top of the line then, divided by the total resistance, which is R1 plus R2 times VCC. And then I get an answer there of 3,59 volts. Difference between VB and VE, there's one forward biased PN junction in between. So 0,7 volts that I have to subtract from the value of VB gives me an answer of 2,89 volts. Then IE is VE divided by RE. 2,89 volts divided by 560 ohms gives me an answer of 5,16 milliamps. Just remember to work accurately to 3 decimals. And therefore I can make the assumption, as I said earlier, that IC is equal to IE or equivalent to IE. It only differs by the value of IB, which is very small in comparison. Then I can calculate the other voltages. Remember VC using Kirchhoff's voltage law. So it's the supply voltage VCC minus the volt drop over RC. I get an answer of 4,84 volts. And then lastly VCE is going to be VC minus VE. But as I said, you have all three terminal voltages. You can calculate the voltage between any two terminals by reading from left to right. That's very important. Remember, if I ask you to calculate VBC, it must be VB minus VC. If I ask you VCB, then it's going to be VC minus VB. Because it's going to affect your polarities. Né? So if you don't keep that in mind, your answers are going to be wrong. But important, this is important, you can mark it NB at the bottom of this example. They say here the basic analysis developed in example 5.2 is all that is needed for most voltage divider circuits, but there may be cases where you need to analyze the circuit with more accuracy. And this we are going to do more often. Ideally, a voltage divider circuit is stiff, which means that the transistor does not appear as a significant load. All circuit design involves trade-offs, and one trade-off is that the stiff voltage dividers require smaller resistors, which are not always desirable because of potential loading effects. Potential loading effects on other circuits and added power requirements. If the circuit designer wanted to raise the input resistance, the divider string may not be stiff, and more detailed analysis is required to calculate the circuit parameters. Alright, So I think at this stage I must first discuss this voltage divider effect with you. The voltage divider. Let me just end the show here first. What now? Voltage divider, or the voltage divider effect, you discussed in electrical engineering 1. But I'm just going to do a simple circuit quickly just to refresh your memory, because this is actually very important. So let's take a simple voltage divider. Got a supply, simple series circuit, 2 resistors, and you can see it looks already similar to the voltage divider that we've discussed in the voltage divider biasing circuit that we've just looked at. So if I have a supply voltage here, let's make that 10 volts, and I have an R1 sorry, I was drawing and you wouldn't be able, you didn't see it. Anyway, I've got a simple series circuit here, voltage divider, 2 resistors R1, R2, so you can already see the similarity that we've discussed with the amplifier circuit. Let's make the explanation simple. Let's make these 2 resistors 1 kilo ohm each. Alright, so what do I know if I have a simple series circuit like this? What is the voltage drop going to be each of these resistors? If I go and measure with a voltmeter over here, so I connect a voltmeter over R2. Remember when we calculated the biasing circuit for the voltage divider bias, we wanted VB, which was also R2. No? So it's similar to that. What did my voltage divider formula say? VR2 is equal to voltage that I want to determine, the resistor I want to determine the voltage over is R2, so it's on top of line over the total resistance times my supply voltage, Vs. Looks similar, nah? VB is equal to R2 over R1 plus R2 times VCC is what we had previously. Anyway, if I go and put the values in here, it's 1 kilo ohm divided by 1 plus 1 kilo ohm, which is going to be 1 over 2 times 10 volts. That should give me a value of 5 volts. You agree? That is what I should get. Alright? Now, let's get to the loading effect story. In electrical engineering 1, when you discuss the voltmeter, you discussed the voltmeter and the ohmmeter and the ammeter and everything. There were some characteristics. The voltmeter's internal resistance, should it be high or should it be low? The internal resistance of the voltmeter. Okay, let's say for instance it's low. Let's make the internal resistance of my voltmeter also equal to 1 kilo ohm, just to keep it simple. I battle to write on this thing. But anyway. What do I know if I have 2 resistors in parallel of the same value? What is the total resistance going to be? Same value, the resistance is going to be half, no? So 1 kilo ohm, I'm going to have a total resistance of 500 ohm. Just for simplicity's sake, let's keep this as equal to, you shouldn't write this, but let's keep it for simplicity's sake, it is 0.5 kilo ohms, no? So if I go and put these values in my voltage divider formula now, remember now R2 has now changed to RT because of my voltmeter. So that resistance is now not 1 kilo ohm anymore, it's only 500 ohms, half a kilo ohm. So now it's going to be 0.5 kilo ohms divided by 1 plus 0.5, which is going to give me what? A ratio of 1 to 3. So now it's going to be a third of 10 volts, which is going to give me 3.33 volts, which is not correct. Why did that happen? That brings us back to Kirchhoff's laws again. Kirchhoff's current law states, if the total current flows into a junction, what's going to happen? It's going to split, eh? It's going to split here, let's call that I voltmeter, and it's going to split into I R2, which is not what I want. I don't want the current to flow through the voltmeter. What restricts current flow? Resistance. So what's going to happen with this voltmeter? This resistance must be much higher. A voltmeter's internal resistance should be much higher. As a matter of fact, a voltmeter's internal resistance is about 20,000 ohms per volt on the voltage range setting. But just to keep it simple, let's make this 1 kilo ohm. Let's make it 100 kilo ohm. That is in parallel now with a 1 kilo ohm resistor. If I have two resistors in parallel and the one resistor is much larger than the other resistor, what's the total resistance going to be? Always less than the smaller one, but if the one is much larger, it's going to be close to the smaller one. So you can go and calculate this. The total resistance is now going to be approximately 999.9 ohms, which is very close to 1 kilo ohm. So can you see now what's happening? If I go back to my voltage divider formula and I put into R2 now 999 divided by 1 kilo ohm plus 999, I'm going to get very close to 5 volts again. Okay, so what happened here, if that internal resistance of the voltmeter wasn't high enough, then it loaded the circuit, meaning that the current is flowing in that direction, which I don't want. I don't want the current to flow through there. I want the current to flow through R2. Okay, so that is the loading effect. And that brings us now back to our voltage divider circuit. If we go and look at our voltage divider circuit again, I actually left the page here. Can you believe it? So what is going to happen here? If we go back to our textbooks, figure 511 there. Figure 511, voltage divider with a load. You can mark there as I did. You can see the one is stiff. How do I check if the voltage divider circuit is stiff? R in base must be equal or larger than 10 times R2. So what should I go and do? I must go and calculate R in at the base. How do I calculate R in at the base? Just a bit lower, there is equation 5.5. R in at the base is equal to beta DC times RE, equation 5.5. So what am I doing here? If I go to this circuit here, there's my voltage divider with load. Doesn't it look similar to the circuit I've just discussed with you? Simple voltage. I can see this R in at the base as my voltmeter, isn't it? As the resistance that is in parallel with R2. Okay? So it's the same thing that happens. Current that's going to split in that direction and in that direction. Okay? So if there's my voltage divider R1 and R2, and I can assume this R in base to compare with the circuit that I've just discussed. My voltmeter, So I have to go and check here because I can see that that resistance is in parallel with R2. Okay, and we've seen I don't want the current to flow too much in that side, né? Because then it's loading my circuit and I don't get the 5 volts that I should have measured, I get 3.3 for instance. What is going to happen? Why is it so important for me? If I go and look again at my characteristic curve, my transistor of IC against VCE with my load line. Now I've done a very careful design. I've designed my circuit so that VB gives me an IB, which gives me a Q point in the middle of the load line, my IBQ. This IBQ is determined by VB. So if my VB doesn't give me 5 volts, it only gives me 3.3 volts, what's going to happen with my Q point? It's not going to be in the middle of the load line. If my Q point is not in the middle of the load line and I apply my signal that I want to amplify in my linear region, what's going to happen? It's going to go into cutoff, which I don't want, and I don't have a linear amplifier anymore. So that is important, that my VB should be correctly calculated. That's why I have to check if the circuit is stiff or not stiff. Okay, how do I do it? Simple. Just clean up a bit here. For stiff, I have to go and calculate. What do I have to calculate first? Here, looking in at the base of the transistor, I have to calculate the input resistance as in equation 5.5. It says R in base. R in base. Remember, these are all capital subscripts, meaning that it is a DC quantity, is equal to beta DC times the value of RE. That's the resistance there, né? Let me just go back. I don't know what happened now. Let's try again. Remember, I'm looking here at this input resistance. Here's my voltage divider. And where's the other resistance that is in parallel with R2? It's this resistance as I'm looking in here. And I calculate it by the value of beta DC and RE. That is what determines the input resistance as we've just seen, eh? Over here. So that's my input resistance. So once I've calculated R in at the base, which is beta DC times RE, I must go and check, is it larger, still larger if I multiply the value of R2? You can see there, R2 I multiply with 10. Then it must still be at least equal or larger than that value. If it is, then I can say that my voltage divider circuit is stiff, and then I can just use the normal voltage divider formula. If it is not, if it's smaller, it means it's going to load my circuit, my VB is not going to be what I want it to be, then I have to take this resistance into consideration. Then I have to go and calculate this RT. This RT, which is what? That RT is now, as we've previously calculated, R2, and the internal resistance of the voltmeter is now going to be, this RT is now R2 in parallel with Rn at the base that I've just calculated. Okay, so now you can see what happens. My formula now changes. It's not only R2, it is R2 in parallel with Rn at the base, which you can calculate separately. You don't have to do it in one step. And please don't make the mistake that the most students do. It is not R1 plus R2 in parallel with Rn at the base. It is R2 in parallel with Rn at the base. Remember, I replaced R2 and R2, so those two values are the same. So it's R2 in parallel with Rn at the base divided by the total resistance, which is R1 plus the value of R2 in parallel with Rn at the base. So if you think you're going to get confused, put a bracket around R2 in parallel with Rn at the base, because that's a separate value. Then I've taken that input resistance into account, and then I will get an accurate value of VB. Okay, so I have to do the very first thing. If I use a voltage divider method of biasing, I have to calculate R in at the base. Why? I have to compare it with 10 times R2 to see that it is still larger. If it is not, it's not going to be stiff, then I have to take that resistance into account. Alright, so if we go back to the textbook again, as I've marked there, you can quickly estimate the loading effect by comparing beta DC times RE, that's the input resistance, R in at the base, to the resistor R2 in the voltage divider. As long as beta DC times RE is at least 10 times larger than R2, the loading effect will be 10% or less, and the voltage divider is stiff. If beta DC times RE is less than 10 times R2, it should be combined in parallel with R2, just as we've seen with the formulas there on top in figure 511. Anyway, let's have a look at an example. Determine the DC input resistance looking in at the base of the transistor in figure 512. This is example 5.3. What do I have to do firstly? Very first thing that I have to calculate is R in at the base. How do I calculate it? Beta DC times RE. The bottom of the page there, in this case 125 kilo ohms. Okay, so remember, that's the first thing that I have to do. Let's have a look at the stability on the next page of the voltage divider bias. They used Thevenin's theorem to analyze this circuit. You've done Thevenin's theorem in electrical engineering. I'm not going to do Thevenin's theorem again. What I want to point out to you, and you can underline this, is equation 5.6 shows the formula here. IE is equal to V Thevenin minus VB divided by RE plus R Thevenin divided by beta DC. But what is important here is that if R Thevenin beta DC divided by beta DC is small compared to RE, the result is the same as for an unloaded voltage divider. So, this is important. A voltage divider bias is widely used because reasonably good bias stability is achieved with a single supply voltage. Alright. Okay, that sentence there, as I've underlined. Please underline that sentence. Voltage divider bias is widely used because reasonably good bias stability is achieved with a single supply voltage. Okay, that's the voltage divider. At the bottom of page 226, you will see there voltage divider biased PNP transistor. Remember, I told you previously, we mostly discuss NPN transistors in this textbook. The PNP is exactly the same. You will see all the formulas are exactly the same. There are some differences, but I'm going to show to you now what you have to keep in mind. We are not really going to use it in this course, but I will show you what you should use. If we go and look at figure 514, you can see there are two methods. The one that I want you to learn is this one. You can see that it looks similar, or it looks exactly the same as the NPN that we've discussed, only I can see now that I am using not an NPN, but a PNP transistor. And what is the thing that I told you previously was going to change? Polarities. So now I have a negative supply voltage. You do get other methods. You can see I can I can use a positive VEE and then I ground the collector. But let's leave that circuit now. I want you to concentrate on figure 514A. The circuit looks similar. You will see that the equations that we're going to use are similar. I just have to keep the polarities in mind. Just for interest's sake, we can have a look at figure 515. You can see this whole circuit here. There's another method. I can still use a positive VEE, but look now what happened. The emitter is now on top. Collector is at the bottom. You can see now RC is connected to ground. R1 is connected to ground. R2 is on top there. So the formulas will differ. If you go and look in the textbook, just for interest's sake, we're not going to do calculations using this. But you can see now VB, but it still makes sense. VB is now going to be what? VB is still with reference to ground. It's still a single subscript. No? So VB is now going to be VR1 and not VR2 anymore. Okay, so it's going to be R1 divided by total resistance R1 plus R2 times VEE, the supply voltage. Okay, VE is still VB, in this case now, because the polarities changes, plus VBE and so forth. Okay, but as I said, I want you to use the method. So we're not going to do example 5.4. I want you to do example 5.5. Let's have a look at example 5.5 quickly at the bottom of page 228. The question there asks, find IC and VCE. What is IC and VCE? Parameters for the Q point. Now remember, the axis is always IC against VCE. For the PNP transistor circuit with these values, R1 and R2 and so forth, but they ask you to refer to figure 514A. That is the one on the previous page that I said that we're going to use, that looks similar to the NPN circuit that we've discussed. Figure 415A, the one on the left hand side, only that the polarities changes now, uses a negative VCC. No? So we're looking at that circuit. Now still, the very first thing that I'm going to do is what? What is the very first thing that I'm going to do? I must calculate R in at the base. Why do I have to calculate R in at the base? Why do I have to calculate R in the base? Let's just go back to that one. Because I have to check if the circuit is stiff or not stiff. Because of the loading effect. Just clean this off here. So we're looking at figure 514A. Okay, so I have to determine VB. I have to determine VB. VB is still VR2, né? So if I go and look at the formula in the textbook, I'm not going to write everything again because I'm not writing very easily on this screen. First thing that I have to do, R in at the base is equal to beta DC times RE. Beta DC is given 75 times 2,2 kilo ohms gives me a value of 165 kilo ohms. Then remember, I have to compare it with the value of 10 times R2 to see if it's at least equal or larger. In this case it's not, so I have to take into account the resistance of R at the base, which is in parallel with R2. As you can see here, the formula that's been used is now VB is equal to R2 in parallel with R at the base divided by R1 plus R2 in parallel with R at the base times VCC. If you did not calculate R in the base and you did not use this formula, your whole calculation is going to be wrong. So please remember, very important, firstly to calculate R in at the base. Anyway, let's have a look at the values. Resistor values, of course, no polarities, but look at the supply is minus 6 volts. So eventually I get an answer of minus 2,1 volts. Remember, I told you, you can look here at the equations. They are exactly the same. You just have to remember your polarities, otherwise your answers are going to be wrong. Next, I calculate the emitter voltage. VE is equal to VB plus VBE. Why is it plus VBE? It's actually still minus VBE. Don't you agree? Remember, with the NPN, we said VE is equal to VB minus VBE. Is that true? In this case, the value of VB was equal to minus 2,1 volts minus, what's the value of VBE? Negative 0,7. Negative 0,7. Remember there? VB minus VBE. That formula is still the same as for the NPN. VB is now minus 2,1 that we've just calculated. Formula the same as the NPN minus, but VBE is minus 0,7 volts. Minus and a minus makes it a plus. That's why in this example they tell you that VE is equal to VB plus VBE, but actually the formula is still exactly the same. You just have to keep your polarities in mind. Alright, if we go back to the book, I can see then I get a value of minus 1,4. IE is then equal to VE over RE that I've just calculated. Take note of the polarity. Minus 636 microamperes. Then I've already told you that I can make the assumption that IE is equivalent to IC, or IC is equivalent to IE, because IB is very small in comparison. So IC is equal to minus 636 microamps, and then I can calculate VC, which is the supply minus the volt drop. In this case, still look at the formula, VCC minus ICRC, but look at the answer. Remember the polarities. Minus 6 volt minus, in brackets, minus 636 microamps times 1,8 kilo ohms gives me an answer of minus 4,86 volts. VCE, the same thing. I've got all the terminal voltages, so it's VC minus VE, which is minus 4,86 volts minus, in brackets, minus 1,4 volts, and I get an answer of minus 3,46 volts. So you can see that they are exactly the same as for the NPN, only that you have to keep your polarities in mind. Alright. So again, this is a very important section. The voltage divider bias, as you can see, is the most commonly used, most popular, most stable method of biasing. So please read through this section. Make sure that you understand this section, because if you're going to carry on with electronics, we're going to use this method again in electronics 2. And we're going to do various types of amplifiers using this biasing method. Also now very important to go and do the basic problems 11 to 18 in your homework books. Thank you.